Alright then, hello guys. Today we're doing another crypto hacks challenge, and the challenge we're going to be doing today is going to be called Modular Arithmetic 2. So what this challenge says, we'll pick up from the last challenge, and imagine we picked up a modulus p, and we will restrict ourselves in cases where p is prime. The integrated modulo p defined a field denoted as fp. If modulus is not prime, the set of integers modulo n defines a ring. A finite field of fp is a set of integers from 0 to 1 and to p minus 1. And under both addition and multiplication, there are inverses of b and b plus and b times for every element a in a set, such as b plus b a plus b plus equals 0 and a times b equals 1. Note that these identities of elements for addition and multiplication is different. This is because the identity when we acted with the operator should do nothing. A plus 0 equals a, and a times 1 equals a. Let's say we pick up p equals 17. Calculate 3 to modulus to the power of 17 mod 17. Now we do the same with 5 to the power of 17 mod 17. What we expect to get for 16 mod 17. Try calculating that. The interesting fact is that in Fermat's little theorems, we'll be needing this and its generalization, and we'll look at RSA cryptography. Now take the prime of p equals 65537. Calculate this number to the power of 65537 mod 65537. Did you need a calculator for this? So we'll be using, I'm assuming, Fermat's little theorem. So we just grab this and go like that. Fermat states that p is a prime number, then for any integer a, then a is an integer of multiplication of p, commonly expressed as a times modulo p. If a is not divisible by p, this simplifies it to this fundamental. So if we look at images, x to the power equals x mod p. This to the power of that is basically x mod p. So it's going to be x mod that and then mod that, I'm assuming. Fermat's little theorem. Okay. See, Python. Because it wants to use Python. Fermat's little theorem is p. Calculate these two. How will you do this calculation? Python function. There's probably already like a Fermat's little theorem is used in Python primarily for parallel testing, for simplifying modular exponential with large number. A simplified and efficient Python function for performing the chord check of the theorem is using the built-in Python function. So the most efficient way to implement Fermat's perturbation theorem is to use a 3-argument version of built-in POW. So a times b times m, a, b, and m function, which computes a to the power of b modulo m. In our case, we could use the Python feature to implement this, where we get, let's see, a and b, which is going to be this value plus that, and then mod 65537, which is the last number right here, modulo m. So let's open up our terminal. Let's open that up. And then let's open up our Kali Linux box, or our WSL for Kali Linux. Wait for this to open up. Just wait for it for a bit. It takes a while. Okay. Python. So we could use the built-in POW function and insert the values that we want or need to use. In this case, we'll just use this first value, and then the second value will be 65536, and then the next one will be exact same thing but with a 7. So if we enter it, we get 1 as the final answer. That gets us 1. I wonder what happens if then we get 1. That's the final answer for this. So if we check the solution, we get the flag was 1. So it's just pretty easy. So this is nothing too difficult, nothing too hard. I guess you just gotta understand that. I guess if you want to implement this function, there's a built-in Python function that you could use to solve this challenge. So nothing too difficult, but yeah, that's about it. Hopefully you guys learned something new today. I know I did, and I'll see you guys in the next one. Peace.